Day 7 today, 7 out of 12 days of new rips. And we talked about scaling laws. Now, scaling laws apply for different networks. Today, we're going to talk a little about scaling language models. And I think mainly we're going to look at hardware and arithmetic and stuff like that, which I think they can apply to other models as well. But okay, so we talked about that before. One of the problems with deep learning in general, that the thing that consumes most of the energy in the GPU and the space in the GPU is the floating point multiplication. So wouldn't it be lovely if we could represent the information in bits, as it does exist, and do build deep learning networks in general with logic gates. So this work over here, Stefan Ormon is a very well-known researcher, has done a lot. He has published a lot of work at NeurIPS. Is not about transformers, but it could potentially be applied to transformers. If this technology that we're going to see on simpler networks can be applied to transformers, it would be great. So what they try to do here is basically use XOR gates, actually logic gates, and I think the rest of it is XOR. I don't remember, but it doesn't really matter. I think if you can do it with XOR and negation, you can do everything. It doesn't really matter. So the idea is really simple. You are reading zeros and ones from images, and you're trying to get an answer. And it turns out, I think they experimented with different architectures, and there seems to be some promise from convolutional neural networks, where your convolution is basically a logical gate. And now you're basically trying to learn that network. That's what you're trying to learn. Whether your convolution kernel, what kind of gate should it be consist of? And the problem, of course, is that it's not a differentiable problem, but they somehow make it differentiable. You can always do, you can always approximate logical gates with sigmoids, and eventually they you hard code. Once you compute it, you get the networks. You use hard logic, and it's kind of interesting how they were able to take CFAR10 and get similar results with other models that require 2 orders of magnitude, maybe 3 in some cases of gates. And I think these are all networks that they actually use logical gates. So if you compare it with floating point, it's even more. So you see here the difference, like it's between 30 to 60 times smaller models per chip area, which is huge. And you can also imagine that you see the speed, it's 1900s faster than state of the art. It goes like from microseconds to nanoseconds. So that's like amazing. You can run the networks very fast at a very low energy. Of course, there's another way of, I remember there used to be a professor at Georgia Tech who worked on analog circuits to do the same thing in the analog domain, which makes it, orders of magnitude cheaper and less energy, and more energy efficient. Now, this talk was hidden between Expo talks. As we said, Expo is usually has to do with the industry, and seeing a talk like logarithmic math in accurate and efficient AI inference accelerator kind of like caught my eye, and I wanted to read learn more about that. And there's this company called, I didn't know them before that, Recogni. I'm not even sure if I pronounce it properly. And they talk about, they motivate and they say, example AI compute rack, not ours, state of the art shipping 2025. 100 kilowatt at peak usage, 200K yearly power bill. And, these are some interesting statistics. Average US citizen consumes 30 kilowatt hours per day, enough to power this rack for 20 minutes. Okay. So your whole year as a citizen is much less than powering up this racks for 20 minutes. Generates 10 minutes worth of AI videos with SOTA models. These are very interesting. I know we're laughing, but they're scary statistics. Text to text might be solved, but only until chain of thought really takes off. It was another prediction. I don't know why they put it over here. And again, we talked about agents, and they claim that agents, the reason why they're not accessible because of cost. We've seen that before. Better models cost exponentially more, but many applications need uncompromised quality, legal trading, media. So, I mean, don't forget that a lot of papers that we see that they have a stellar performance, if we had to run them everywhere, we don't have the energy to do that. So, another, the same issues is highlighted. And it's coming up more aggressively because if you think about it, media gen has matured. So media generation, what I mean here, facing very high cost issues. People love generating images, and think about how much time and bandwidth gets allocated to GIF or GIFs or images that people exchange. I imagine how much they want to generate their own stuff here. And here are some other statistics that a single HD image costs 10 cents. An hour of 4K video generation is more than $100. And there's no system that can generate videos in real time. Hence, you can have a human AI conversation with a human, like with visual. So social media is starving. It's very hungry for Gen AI, for images, but they basically cannot use it. But I'm sure they want that. And video and image generation requires 16 bits of precision. And okay, they claim here, let's give them the opportunity to advertise, to reduce the media generation cost by more than 10x, thereby enabling new AI media-based business models and products. That's kind of like a bold movement. And here's kind of like their motivation. So basically, they show you stable diffusion and different quantization. What they're trying to tell you is, yes, you can try to quantize your models, but notice how bad the performance becomes from 16-bit to 4-bit. It's like significantly worse. So, and they have several examples. This is another thing depicting a galaxy, and you can tell it's really becoming very bad. So, just simple quantization is not really sustainable. But I have to say here, it's not as bad as in previous examples, but you can tell that it's not what you want. And, logarithms to the rescue. So basically, as we described, as we said in the beginning, our problem is how are we going to do A times B fast enough? And we know that we can take we can write this as 2 to the log 2 of A times 2 to the log B. So basically, we can do additions in the logarithmic domain, and then in the end, we can you can exponentiate that to get the true value. If only things were that simple. And as you guessed, in AI, multiplication is part of it. Well, first of all, computing these logs and make sure that you're doing the right allocation of bits. Not an easy task, but not unsolvable. But we also have a C component. So even if we can write as 8 times B as P you compute it, then you have to do C. And that's a problem, okay? This is cheap, this is addition, but the problem is that you have 2 to the A times 2 to the B, and then you have to add plus C. And, you know, we only have log P in memory. So, you know, you can work out the math and you can put some Taylor expansion, and, you know, you can come to the rescue of lookup tables. They go through the math. It turns out that you can do it, you know. So the problem is that you do it, but once in a while, you know, the system, so you can do it, but it's unstable, okay? So you can always get some places where that kind of approximation doesn't work. And the bigger the model gets, the more outliers you have, and they're getting harder to quantize. Well, if you follow the talk, they do explain how they come up with we solve that problem, and they basically, you know, claim that we want to keep complex quantization methods away from the user. They offer 100% high trust fallback solution, full FP16. So I think their solution is we're trying to do it logarithmically. If we don't, then we fail over to 16-bit. And this is what they present. Now, I'm not really in a position to judge. So I think the NF4 is theirs. They claim they get better results. I think here things look more stable with the log math. And the summary is that even co-pilots, not even pilots, even for co-pilots, the reasoning bias introduced by sometime poorly performing AI model is destructive to the overall process. I don't know why they came up with this example, but for an actual product, users need 100%, okay, they get a now safe fallback choice that will guarantee uncompromised quality. So I think probably the innovation here, everybody can do the math, but they've probably done the engineering work to kind of like offer fallbacks when that fails. Our log math Pareto, as they call it, offers true uncompromised 16-bit quality. They have a tiny drop, 0.01%, the way they measure it, at the same efficiency of 4-bit deployments, and mixed precision quality, 0.02% drop at the efficiency of 2-bit deployments. So, you know, it's an interesting direction. We would like to see more. Okay, so this is a very pleasant talk from Microsoft Research. It was an invited talk. You know, there's probably 3 or 4, maybe 5 invited talks at a whole in Europe that they are global. These are also very prestigious if you get invited. And they're usually very high quality. Whenever you get accepted or you get called for that, you spend a lot of time presenting that, preparing that. Sorry, I did. Okay, what happened here? So Microsoft has come up with the era of the BitNet models. It's a bit glitch with the slides here. And these are the papers that they basically need to BitNet. You can take a look at them. And let me see, because I think we might have missed something. Nope. Yeah, I think we're fine. Yeah, well, it's my fault, I thought. Okay, so we're seeing this slide again, but I will repeat it. Scaling laws in AI. We study empirical scaling laws for language model performance on the cross entropy laws. The law scales as a power law with model size, dataset size, and the amount of compute used for training, with some trends spanning more than 7 orders of magnitude. Scaling folklore in systems. You can't scale by throwing hardware at the problem forever. Scale exacerbates hidden flaws and inefficiencies. Everything fails at scale. Scaling is sublinear. Scaling requires revisiting assumptions. Again, at some point, you find the law, you exhaust it, and then you also go back and you start fixing things. One of the pillars of that presentation was about efficiency. AI will reach new levels of efficiency, approaching natural intelligence, and become deployable on pervasive devices driven by co-innovations in model architecture, software, and hardware. And this is a really great slide generated by GenAI. And we all know about the AI winter. So neural networks came in the 90s. They overpromised, they underdelivered, and they were shut down. No more research was funded for that, except for a few people like Hinton, that was, and others that they were slowly, and Hochreiter kept working silently, and they became famous again after the summer of AI came. But what we neglect, or we don't think, is that as the AI was sleeping, the Sleeping Beauty over here, a lot of things happened in the system worlds that they basically prepared the scene, and they set the scene for AI success. And we have multimedia, which means that people start producing images that we wanted as training data. The World Wide Web, okay, which means that we started passively, like where did the C4 dataset, which is the most common one that people train language model, come? People started publishing more and more, and the web search helped us scrape and organize that material better. And big data, I mean, right now, when you are training models of 1 trillion parameters, you need big data technology to mine. And where is this big data technology going to be stored? On the cloud. So we need huge cloud infrastructure. So the fact that the Googles, the OpenAIs, and the Amazons, and the Metas can do that is because they have cloud infrastructure to do that. So when AI woke from the hibernation, we had in our fingertips all this, technology to use that didn't exist in the 90s. Okay, so let's not forget that. And BitNet, basically, it's not a 1-bit architecture, it's a 1.58 bit, okay? And it's basically you're quantizing in 3 levels, -1, 0, and 1. And you see that you take a toll on the loss in smaller models, but as the models become bigger, the gap narrows and it vanishes. Now, I've heard some criticism on that. I have to say, there's a company called Neural Magic that their job is to sparsify language models, deep learning networks in general. And that was kind of a direction. Maybe we can keep the 16-bit floating point architecture, but sparsify the network so that we have less multiplications to run. I think that's kind of like the premise that Neural Magic talks about. And when I asked them about BitNet, they said, well, you got one version of BitNet, but do you have like Llama in BitNet quantization? And do we have a way of taking any language model and deploying that in that architecture? So, I mean, I hear that, but I can see Microsoft putting more resources and coming up with a resource, like with a framework for doing that. There is definitely a lot of interest, and there's a challenge. Because the truth is, you won't see BitNet in any practical application. Again, there's another reason why, because BitNet, you cannot fine tune it, okay? But the idea over here is when you go to that low quantization, you can use addition plus lookup tables and be very fast. And
what does 1.58 bits mean?
It's like log of 3. That's why, because you have 3 levels. If you have 2 levels, it's 1 bit. If you have 3 levels, because it's 0, -1, and 1, the log 2 of that is 1.58, I think.
Okay, interesting.
That's really well done. And so you can see there's a significant drop in the consumption. And in area cost, look at that, just, I don't know, 1,000 times, I don't know, 200 times, something like that, less. And surprisingly, you can you can see over here, this is the model inference on Apple M2 Ultra CPU. The energy cost is 70% down, and the inference speed, tokens per second, is pretty high. This curve, like the red one, is human reading speed, which basically means that you can have 100 billion, which is quite a big model, generating tokens at the rate that you can read. So you make it real time, basically. And 100 billion model can basically fit on a chip right now. And of course, the problem is that we don't really have TPUs that they have this kernel of addition plus lookup table efficiently implemented. So that's why they think that we can reach, if we can make that 20x teraflops per square millimeter, okay? And in my opinion, this basically opens the door of, so this is the BitNet at 4.8. Opens the door of going to even a trillion model on a chip. Okay, now I'm going to talk about another paper that I like, which I talked about that in other talks. Like, keep in mind that these talks are supposed to be standalone. So if somebody wants to watch that without the previous one, they shouldn't assume any prior knowledge. So I know some of you have watched the previous one, so you might find some repetition. And the idea over here is that I mentioned before, what motivated the invention of the second layer in multi-layer in perceptrons was the fact that people complained that it cannot solve the XOR problem. And if you add the second layer, then you can solve the XOR problem, which, the XOR problem is the simplest parity problem, like counting the number of zeros or the number of ones. Now, this paper, this talk talks about, trying to solve different parity problems, like find out, the ratios of zeros and ones, or, how do we have even or odd? So there's even different parity problems. And they realized that, the best way to, these are great problems to help you understand the faults of your architecture and fix your model. I would focus on that curve over here that shows that we had a 15,000x increase in 5 years. Deep learning surmounts various computational challenges to produce impressive results that we didn't expect. Synthetic setups that replicate phenomena in large language model that we can track experimentally are very important. And here are the challenges. There are numerous knobs to tune in a model. Cost is too high to carefully evaluate the impact of choices. And it's hard to isolate different components. And the approach here is create synthetic setups that replicate phenomena in large models while being tractable mathematically and experimentally. And this is what this tutorial, it's a very long tutorial. These are today's synthetic setup, learning sparse parities. And, one of the things that, so here are some papers that they talk about that. And the thing that we are trying to understand here is the emergence. Emergence is like, people realize that as you increase the size of a language model, all of a sudden it starts like showing a behavior that you couldn't see in smaller scales. It's kind of like sudden. It's not kind of growing linearly. Of course, there's papers that have disputed that, but let's not get into that debate. And distillation is another issue. Here is the mathematical problem of learning sparse parities. And the output is a subset of relevant variables. So it's, XOR is one output, which is +1 or -1. Here it can be, it's a Boolean function, basically. And again, going back to the XOR problem, in fact, it's interesting that convinced everyone to abandon deep learning because they weren't calling it deep learning, and here you see the frozen. And then that was, people took the challenge and they solved the problem. So recently gained interest experimentally and theoretically. So similar problems of learning single index and multiple index models studied over Gaussian input. So that's probably something that existed before outside of the context of language models. And I don't want to get into the details, but again, this is more like of theoretical importance / practical towards the end. But the question is, can neural networks learn sparse parities, and when? And it turns out that one of the outputs that we got is that I can't remember from which paper, we've seen this before. People on by studying a parity problem, they came up with this law, like you can predict the laws based on these parameters. But I think it depends on a specific problem. Another problem is, can a bigger teacher help a smaller student learn faster? Progressive distillation, train a student model using the predictions of progressively stronger teacher models. So, for example, Gemini 1.Flash is progressively distilled from Gemini 1.5 Pro. Outperforms per Gemini 1.1 Pro on 41 out of 50 text reasoning tasks, and achieves 95% of Gemini 1.5 performance on average. So this is another problem that they're trying to solve.
What are the relative sizes of the Flash and?
It's probably significantly smaller. I don't have it offhand, but I wouldn't be surprised if it's like 10 times smaller. Because usually that's the difference between the Pro and the O, or the Mini, as they call them. Sorry, in GPT has the same. OpenAI has the 4.0 and the 4.0 Mini. And the same thing holds. Even the same thing happens with llamas. They do first the big one, and then they distill it into smaller ones. And the same thing happened with DeepSeek R1. It was kind of distilled from the bigger model. Some other use cases is understand why grokking happens, essential building blocks for several reasoning problems, useful for understanding the benefits of chain of thoughts, model spurious core features to understand robust learning. I have to say this tutorial didn't have a good referencing system, so it took me a lot of time to find all these references. But I think it's worth digging into them. Again, this is something that I kind of scratched the surface over here. It looked very interesting. I encourage people to study more about that. You can see here teaching transformers, modular arithmetic at scale, length generalization in arithmetic transformers. What can transformers learn in context, a case study of simple function classes, the evolution of statistical induction heads, in context learning, Markov chains, how transformers learn causal structure with gradient descent, grokking, generalization beyond overfitting on small algorithmic data sets. These are all very interesting experiments that I think the practical aspect for that, so as a data scientist, or should I call myself language model scientist, I think that by reading this paper and seeing these experiments, it can help you debug and understand what's going wrong with your model. So this is what I call as a very useful curriculum to have as a background to be a language model scientist. And, of course, here are the references if you want to click and get them. So we are on time. Tomorrow we're going to have, I think it's a big lengthier presentation. It's going to be about the large language model scientist toolkit, and what I talked about, the new, in my opinion, emerging role in the companies.